Just a minute, just a minute. I hope you are all well after this long period on the New Year. Okay. Okay, it seems to be okay. So I move to my pulpit. Okay. Okay. Can we start? Okay, so today, hello. Can you hear me now? Is everything okay? Okay, thank you. Sorry for this delay, but I don't know what's happened with my computer. Okay, so as I said in the beginning, today we are going to the second part of our lecture. So we are going towards the sensor and the transducer. So today I'm going to tell you something about metrological properties of a sensor. We can classify and define the words sensor and transducers. Okay, so and first about the exam. So as I was talking on the first lecture, I proposed a zero exam on our last lecture, so on the 29th of January. So it will be the zero exam. So this is just an additional time for you to pass the exam. And then in the session, we've got two terms of the exam. So the first is the 11th of February. Let's say we can start at 10, and the last one is the 9th of February. So also we can start at 10. If anybody can't use these terms, so please contact me, but I hope that you got 3 times, so you can choose which one you prefer. Of course, it's probably easier to pass it in the zero exam. Okay, so this is the exam. Okay, so let's back to our sensor and transducer. What are the sensor and transducer, and what are they for? First of all,
sorry, one question to the exam. Yeah. So how long is it going to be?
The exam?
Mm-hmm.
I don't know. I think it's 1 hour, 1.5 hour. It should be enough. It's just a test.
So no open questions, just a test.
There are some open questions, some simple calculations. So I hope 1 hour, 1.5 will be enough to pass it.
And would we need to draw circuits or just like not really?
You know, in the last time, because we had a similar situation, I pass a file. Which you could fill in a Word program or any program you wanted. You use for addition. So you do not need to draw anything there, but just to write some write some answer or write down some calculation or just the number of the answer. Okay.
Okay. So
some of them will be closed, some of them will be open. I think the half and a half probably. So this is just a word file. So you will feel it. Okay. One will end in I don't know 15 minutes. One will end in 1 hour, but I think it should be enough 1 hour. Okay.
Okay. Thank you.
Thank you. So going back to our problem. First of all, the order of electronic circuits or the system is to perform a useful task, or function. So, of course, we can build an electronic device which will do nothing, but it's not useful for us. So generally, we build some system to do something. So the system. So if we want to build a system which does something, it should communicate with us, yes, with the or with the world, yes, the environment. So it can be communicated in the real world, whether it is by reading or reading some input signal or some other type of activities, and make some output changes. So we need something which feels what's going on in our environment, and some elements which show us what's going on or which changes something. So we need an input and an output. So as it is written here, in other words, the electronic system or the circuit must be able to be capable to do something. And the sensor and transducers are the part of the system that can perform this situation. Yes, this is the element. This is sensor and transducer are the elements that can connect the environment to our electronic system. So generally, it is not easy to explain what is the difference between transducers, sensor, and actuators. But generally, transducers, which means something what transduce something. So transducer can be categorized by the direction of information passes through them. Okay, so we've got a sensor. So it means that the information is coming from an environment, so from some physical or chemical or another type of changes. So we can sense them. So this is the sensor. This is the part of transducer. This is the sensor. So it feels what's going on from outside. And an actuator. An actuator is the part which do something, some outside. So it's, I don't know, for example, start hitting, start moving something, start showing us the information. So generally, the information from outside is going to the sensor, and actuators gives us some outside elements. So it makes some movement or something like that. Or, of course, we've got some bidirectional transducer, which means that it has some meaning that we've got the same situation as an input and an output. So a sensor is the part of the transducer, again, that can stimulus from the physical or chemical system. Yes, so we can measure, I don't know, temperature, we can measure distance, we can measure some chemical changes, some amount of weight or something like that. Okay, so generally a sensor produced a signal which represent information about the system. the outside system, of course. And this is used as a type of information for control system or telemetry system and another system we designed. Yes, so a sensor gives an information from outside world. An actuator, as I said, it is a device that responsible for the controlling a mechanism or system. So it changes something. It is controlled by a signal from a control system or manual control. So we've got manual actuators and system control actuators, or automatic control actuators, as we can say, or actuators that are controlled by the sensor. This is the most typical situation. It is the actuators. It is operated as a is operated by a source of energy. So generally, actuators need external excitation, external power supply that can move or heat or something like this. Okay, so they can actuate something. So this means the mechanic that the actuators can change our energy into mechanical force, electrical current or voltage, hydraulic rod pressure or pneumatic pressure, and other different changes of energy. So generally, an actuator is a mechanism by which a control system acts upon an environment. So, okay, so these two kinds of these two parts of the transducers can be divided into active and passive. Of course, this is just you can say it's passive or active only up to sensor, because the actuators are generally supplied. So active sensor required an external power source to operate, which is called an excitation signal or external supply. The signal is modulated by the sensor to produce an output signal. So the physical or chemical changes cause changes in the output signal of the sensor. This is why we are going to measure some environment changes. Of course, passive sensor, the passive sensor is this part of sensor that do not need an external supply. So the current or the voltage is generated directly from the physical changes of physical or chemical, okay, without any additional energy. Of course, nowadays we've got many different types of sensor. I hope you will discover more and more in your life, and during your life will be discover more and more sensor and transducer, because this discipline is going to be the most important in our environment. So we've got many types of transducer, as I said, active, passive, and active, but we can divide them also by the output, what kind of output signals available. So we have analog, this is the simplest one, and the digital one. This is probably the newest way to move this signal from the sensor to the system. Okay, so we can divide to analog and divide digital, passive, and active. Of course, the passive sensor are generally analog, because if we want to move them to the digital one, they need to be transduced inside, because generally the physical or the chemical changes are not digital, so they are analog. Of course, we can divide them as a type of input or output transducer being used. Usually depends upon the type of signal of process. So this is up to you, up to your knowledge, which kind of sensor or which kind of transducer you will use. So generally, we can define a sensor and transducer as a devices that convert one kind of energy or physical changes or chemical changes. So we can say it's a quantum of energy into another quantum of energy. This is general. Okay, so there are different sensors and transducers, and we need to describe them, how they behave and what can measure. Okay, so this is a generally definition of specification. They are used to describe the sensor and transducer. So first of all, we've got dynamic range of the sensor or transducer. We've got accuracy, linearity, precision, repeatability, noise, or hysteresis. I will describe each type of this problem. So the first one is dynamic range. And typically, we can say this DR or DNR or DWR. So if you will find out in the manual, in the datasheet, some words, DR or DNR. So it means it's dynamic range of the dynamic range of sensor or transducer. And dynamic range is the ratio between the largest and the smallest value that can obtain by the sensor. So if we've got a sensor, for example, for temperature, and we can measure from the sensor can measure from 1 Celsius degree to 100 Celsius degrees. So we've got dynamic range from 1 to 100. Okay, so it's 100 dynamic range. Of course, the dynamic range can be described not only by a digit, like in this example, but also in the decibel scale. So we can describe in the decibels or bells, as we wish. So the logarithmic value is more commonly used because generally the width of dynamic range is higher. It's not a simple small number. So the dynamic range is in decibels. Okay, the repeatability or test resets reliability is the closeness of the agreement between results of successful measurement of some measurement carried out. So if we measure something, the repeatability is the measurement that are taken by, for example, a single person, but maybe not a single person, but a group of persons on one instrument on the same item under the same condition in the short period of time. So if we will measure, for example, I know value of voltage on the cell using a voltmeter, the repeatability is the difference of values we can obtain by using this voltage. Okay, so but it must be in a short time because we do not need to that another environment properties will change, like example temperature of the room or the heat of the measurement voltmeter. So generally repeatability is made in the short time by one person on the one item on one instrument. Okay, precision is the amount of information those converse take place by a number of items of its digits. So if we got this voltmeter and we've got 4 or 3 digits, yes, so we 0.01. So it means this is the smallest value. So if we measure something, we can obtain 0.01 or 0.02 or 0.03. So the precision is this is the number of items of each digit. So the precision shows the closeness of 2 or more measurements they have to each other. So if we've got 0.01 and 0.02, so the precision is 0.01. Okay, accuracy. The accuracy has 2 definitions. This is description of the systemic error of a measurement of statistic bias. So it means that you probably had some experiments with the measurements. So you should know that if you or your colleague will measure the same value, it can happen that the voltmeter or some other kind of measurement system will show you different value. This is caused by some external elements, some the human, because each of us can measure in a different way, can take the sound in the one or another hand. We have different temperature on our hands, so we change the property of the measurement system. So general accuracy is the statistic bias of all these errors. So we can measure. So we can measure something with some error, and this error is made by statistically measured, and we can have the accuracy of the measurement. So this is the accuracy is generally the difference between the results and the true value, but the true value is never known. So we can measure some measurements. We can do some measurements, and by some statistic calculation, we can say what is the, let's say, true value, because we never know what is the true value. Okay. So, for example, when you are measuring the value of the resistance using a digital multimeter, we have a resistivity of is actually 25 ohms, but multimeter shows 43 ohms. So it means so multimeter is precise but not accurate, because the precision is, let's say, 1 ohm, and the accuracy, as we can see, is 2 ohms. So if we made the calculation, for example, to time, we can calculate what is the, let's say, the real value of the resistor. So we've got the precision. Yes, we've got the accuracy, the precision, and the accuracy. Yes. Okay. The next problem is the hysteresis of the measurement, because if you are in our real world, we have some problem, some different, because the physical reaction, the chemical reaction are not stable, so we can't measure. If we use to measure something, we change the process generally. So it can occur that we have some hysteresis. So if we measure, for example, a temperature, let's say this is the temperature. So if we're using some sensor measure the temperature in one way, going from the lower value to the higher value. We are going on this curve, yes. But if we are using the same measurement, using the same sensor, but we going from the high, let's say, temperature to the lower temperature, we will go on this way. So we've got the hysteresis, which also is an error that goes to the accuracy properties. Okay, so generally in the accuracy process, in the accuracy in the data sheet, it is the sum of all the errors. So the temperature dependence, the measurement system, which is if it is dependent from the outside temperature, or it has a hysteresis, or can have some human error. So generally, all of these elements goes with the precision in the accuracy of the measurement system. Okay, so here we've got some examples. I hope you can hear me. Can you hear me?
Yes, you can.
Okay, thanks. Because I'm talking. Okay, so here you've got some examples of the. Here you've got some physical changes, physical elements, and the example of sensor and actuators. So let's say you got the measurement of the light level. We would like to measure what amount of light comes to us. So we can use different sensors. We can use light-dependent resistor. We can use photodiode, phototransistor, or solar cell. Yes, and these parts are the sensor. And as an actuators, we can use lights on lamp, LEDs, display, fiber optic. Yes, so these are the example of actuators for light. For example, but for temperature, we've got thermocouple, thermistor, or resistive temperature detectors, and as a actuators, heat, fan, or something like this. And for force, position, speed, and sound, we've got different kind of sensor and actuators. So you can see it on this table. I'm not going to discuss maybe it later because we've got as many sensors and a lot of transducers and a lot of actuators. So it's up to you what kind of the problem, what we want to measure and what kind of transducer we will use. Okay, so I would like to show you something more deeply about the temperature sensor. It is just an example of, because I could use any type of physical changes, but the temperature sensor is very useful to show you the difference of the transducers, the difference of the sensor, and what physical properties can be changed from the heat to the voltage or to another kind of energy. Okay, so generally, temperature sensor should measure the amount of heat energy or even closeness of is generated by an object or a system. Yes, so we've got a system or object, and we would like to measure the energy, the temperature, which means the energy of the object. So, as I said, we can use different kind of sensor. We can use analog, digital. So, first of all, we can divide the temperature sensor into two physical types, or maybe well, let's say it's general division. So we've got contact temperature sensor. So this is the part of sensor that needs to be glue on the system. It must be physically connect with the measurement unit. So, and non-contact temperature sensor, and this is the type of sensors that I use, the radiation, the conversion and radiation of the monitored element. Yeah, so we know that the temperature is connected with the electromagnetic radiation, as it was said in the example of the black box, heated black box. So generally, if some elements have the temperature in, generate an electromagnetic fields in the infrared position. Okay, so we can measure all directly the temperature. Let's say it's directly, so it's connected, but we can measure it indirectly by the measurement, the radiation of the object. This is the example of the element that is the simplest element to measure maybe not the value exactly, but to measure the heat, to measure the temperature. Because if we use two metals, yes, which had different properties, different properties regarding the temperature. So if we heat this metallic element, so one will, for example, will be stable, and one will be longer if we heat them. So it causes that the element will move and open, for example, open or close a circuit. Okay, so this is the thermostat. This is, we can say, this sensor, the thermostat. And if you use these two different materials, we can produce an element that can transfer a heat into the maybe not, it's not the energy, but it can open or close the electrical system. Okay, so we can sense if it's over the temperature or under the temperature which is set for this special kind of metals. Okay, so this is on the one hand, this is a sensor because it senses the temperature, and we can say also it's an actuator because we can move something to open it. Okay, so this is the easiest temperature sensor, but not the last. Okay, then another type of the temperature sensor is the thermistor. The thermistor is another type of temperature sensor. The name is the combination of the words therm, alloy, sensitive, sensor, istor. So it is alloy, sensitivity, sensor, so it is thermistor. The thermistor is the special type of resistor which changes its physical resistance when exposed to the changes of temperature. So we suspect, using some kind of material, that it changes its resistance properties due to the temperature. And thermistors are generally made from ceramic materials, such as oxides of nickel or manganese or cobalt, and it has properties that changes the resistance due to the temperature. This is so we've got two kind of temperature. We have generally two kind of thermistor. One kind is NTC, it means the negative temperature coefficient, and PTC is a positive temperature coefficient. But typically we do not use the positive temperature coefficient. We generally use the ceramic cause that we can produce the negative temperature coefficient, so it reduces the resistance due to the temperature. Okay, this is the example of the thermistor. So as we can see, if we increase the temperature, we decrease the resistance of the thermistors. So it is the NTC thermistor, and generally are similar. It is the main value of the NTC is this value, so 100 ohm or 1 kilo ohm. It means that we've got the resistance in the at 20 degrees. Yes, so we get different. Of course, we can produce different thermistors, but each of them are set for a special voltage, and we can measure the difference between the voltage. But if you can see, it's not linear, so it's useful, but we have to linearize the results for NTC transducers. So the thermistor are also used to protect the system from the overcurrent or overheating. So this is the chart how NTC thermistor behave if we use it in the series of the load. Of course, if the temperature will increase, the voltage will be decreased, but it also, you can have a time chart. So if we move the current, yes, the step of the current, the thermistor cause that it is smoothed. Yes, this is because it starts to heating and changes the resistance. Okay, so sometimes use thermistor to protect the load. Okay. Another kind of measurements of the temperature is the thermocouple. The thermocouple is generally the most commonly temperature sensor nowadays, or maybe not nowadays, but generally they are commonly used everywhere. Why? Because thermocouple is very simple. It uses just two elements, and it is very speed and response of change in the temperature due to minimally of the size. And generally, the thermocouple is the passive element, so it's generated an energy, and we can use them in the wide range of temperature, even below 200 Celsius degree or over 2000 Celsius degree or more, even more. So generally, thermocouple is the connection of two metals. In this example, we've got iron and constantan, and we've got an element which is heated. So the join of these two wires is the elements that can measure the temperature. And because we've got different materials, different Fermi levels, So we've got different voltage outside of this junction. If we heat it, we can different voltage, and then we can measure the output voltage. Generally, the lower one is the reference or the ground. Okay, so this generation of the voltage is connected with the Seebeck effect. Is the conversion. This is the conversion of the heat directly into electricity, and it was discovered in the 19th century by Alexandro Volta. So it is very old sensor. So generally, if we fused together the join of two decimal materials, so two different materials, the production of thermoelectric energy effect, which gives us constant potential voltage. Generally, it is not very high voltage, but it is in millivolts, and we can amplify this voltage. So the Seebeck effect is a classic example of electromotive force, or so the leads are connected, for example, to the measurement system. So electromotive force, of course, by the Ohm law, is generated by the current, even it is absence of the voltage difference. So the energy is equal to the local voltage and the local conductivity. So we can generate an energy. This is the Seebeck energy, and we've got the Seebeck constant, and the difference of the temperature. So Seebeck constant, of course, is different for different connection, different materials, but we know what we can measure this, and it is tabulated. So we can calculate the energy which is connected with this sensor made of two kind of metal. Okay. Okay, so we've got as I said, we can use different materials, different metals. So we have to classify them. So we can classify the thermocouple by the color. So if you find something which is brown, it is nickel, chromium, and constantan, and this is the A type of thermocouple, and we can. This is the sensitivity. This is the range of the. This is the range of the temperature we can measure. So, as you can see, we can, for example, nickel chromium constantan. We've got iron constantan, and we can measure voltage temperature over 0. And, for example, nickel chromium and nickel aluminum. So we can measure higher temperatures, and this is red, and the N type is the yellow. Okay, and any others solution, copper constantan, copper nickel. So we can connect any type of metals we can, but they should be able to generate the voltage. But generally, if we are using this type of combination, we are trying to have the linear difference between the voltage and the temperature. So, as I said, it is the voltage from the thermocouple is very low, so it's in millivolts. So we generally need to amplify them. and we use an amplification as we were learning before. Okay, so that was the thermocouple. Now we are going towards the resistance detector. Maybe it's similar to NTC, but NTC sensor were negative coefficient sensor, and the PT100, PT1000 are the resistance positive coefficient sensor. So the relationship between the temperature and the resistivity of the element is made in by this equation. So this is the resistivity at temperature 0 and the changes due to the temperature. So of course it is obvious that each kind of metal, of each kind of conductor has its different properties, which changes the resistivity changes the resistivity due to the temperature. So here you've got some coefficient for the gold, for example, for the copper, nickel, platinum, and so on. But if we measure the difference of the resistance due to the temperature in the wider range of the temperature, we can see that some of them are linear and some of them are not linear. So, for example, the nickel that was used in the if we use a nickel as a measurement, so we can see that we've got some parts that are not linear. So we can use nickel up, for example, 500, but we can use the copper and the platinum in the wider range of temperature changes. But generally, why we don't use copper? Because we would like to have an instrument that can measure temperature in a very wide ranges. So copper is not very good as a material because it can oxidize, it can change the mechanical properties, it can oxidize, it can we can't do the copper sensor in the higher temperatures. So generally the gold standard for the measurement was taken by platinum changes. So the PT, it means platinum for the sensor. If you can find some PT sensor, it means the platinum sensor. 100, it means that it has 100 ohms at 20 degrees. Or we can, another part is PT 1000, it means that we've got 1000 ohm at 20 degrees. Okay, so precision. The absolute stability of this type of sensor is also quite high. So if we use platinum sensor, the stability, the precision is very high. And it's, for example, at 300 Celsius degree, the tolerance is 0.75 Celsius. So we can, the linearity, the stability, the precision is very high. Of course, if we increase the temperature, up to 1000 Celsius degree, the tolerance is a bit higher, but it still has more or less 1%. So for as I said, it is the one PT100. It's set. It is a gold standard, so you can measure the temperature changes with extreme precision, because the changes of the resistivity we can very high. We can measure very in a high precision, so we can measure also the high. We can have high precision of the temperature measurement. So generally, the PT100 we can make a system that can measure the temperature, for example, up to 0.1 Celsius degree. So it's very, maybe not with extreme precision, but very high precision. But of course, we can measure, we can produce a sensor that can have very, very precision of the temperature measurements. So okay, we've got different type of PT100 elements. Generally, they are a bit larger than those of thermocouples. I will try to show you. To show it. But 100. Okay, and we can graphic. Let's say. This is. Okay, it was said that the PT100 term is I'm sorry, I just moved to the example of the sensor. So this is the example of PT 10,000 in a matter of fact, but you can have this the same sensor in PT100 or PT1000, and generally, if you can see, it is very, very small case, because it is SMD 8.5, so it generally have 3-5 millimeters long. So if you can see, we can produce a PT sensor also as a small device, but generally they are larger. This is the typical. This is a typical solution for the PT100 element. So it's longer, but it has, as I said, very good temperature measurements. First of all, it's linear, and it has a very good precision. So it is longer than the thermocouple, but it is a gold standard and used to measure a very precise temperature changes. Okay, so what's the problem of the measurement using resistance elements? I'm sorry, I'm on a different computer, so I can't show you on my OneNote box. Okay. So what is the problem? The problem is, if we, let's say we have none of these elements. Okay. So if we've got a resistor that changes its value, so we can connect it to external source, yes, and if we add some resistor as in series, so we've got the changes of the voltage. Yes. The changes of the voltage are caused by the changes of the temperature, of course, but the changes of the voltage using PT elements are it's also very small. It's milliohms in the matter of fact. So we have very small changes of voltage here. Yes, because if we divide this, even we've got the same value of the resistors, for example, 100 here and 100 here, so we divide it by 2. So we've got millivolts here. And if we would like to amplify it, it is of course possible, but difficult because you got a larger voltage here and the small changes of voltage here. So what is the solution? The solution is to make a reference voltage. Yes, if we add another branch of resistors which are similar to those one, let's say 100 here, 100 here, and 100 in 100 here. So in this situation, at 20 degrees, we've got the difference of the voltage here and here is 0. Yes, because we've got all resistors are at 100. So if we divide it by 2, so we do a half of the power supply here and a half of power supply here, and we can use a differential amplifier to measure the difference. Okay, so if this solution, it's called Wheatstone bridge, because Wheatstone discovered that we can use four elements to minimize the difference. Yes, to find out the zero voltage at zero measurement. Okay, so do remember the Wheatstone bridge. Okay, okay, that was the end of the temperature measurement. Now we are going towards the strain gauge. Okay, can you tell me what is the time, because I do not have any. Okay, we've got some time. Okay, can you hear me still?
Yeah. Yes, we can.
Okay, thank you very much. Okay, so now we are going toward the strain gauge. Strain gauge is one of the most widely used strain measurement sensor. Yes, this is the strain gauge. Yes, this is the strain gauge. It's use the changes of the mechanical changes of the strain, changes the resistive parameters of the element. Yeah, generally, we know it because we've got longer wire, it has higher resistivity. So if we use the same knowledge and we produce a strain gauge, yeah, so if we use very small strain gauge here, yeah, this is the wire, yes, this is our wire, and we use, for example, forces to change the mechanical properties of this element, we will change the resistive properties of these elements. Okay, what we've got here. Okay, yeah, this is the relation between the changes of resistivity due to the changes of the strain. Yes, strain factor and the changes of the resistance. This is the strain. This is the strain factor. Okay, I try to show you a film. Okay, let's start from this time. Can you hear something?
The film is muted, I think.
Okay.
The diameter of a human hair is 80
okay,
to 100
okay.
micrometers.
Sorry. Oh, today I've got some problem with the muted.
The production process begins with a metal foil that is thinly rolled to a layer size of 3 to 5 micrometers. As a point of reference, the average diameter of a human hair is 80 to 100 micrometers. The foil is connected to one side of a carrier material. The other side of the metal foil is covered with a light-sensitive layer. A photographic negative of the grid design for the gauge being manufactured is put on top and exposed to light. Where light goes through the negative, the meandering grid is hardened. In the development process, the non-hardened parts are washed away. The individual gauges are then separated from the sheets of gauges and tested to verify that they meet the specifications, and a correction factor is defined. The principle of the strain gauge is this. A mechanical stress on a strain gauge causes a deformation of that gauge. Since the material is tightly adhered to the article under test, the gauge acts like the material that it is attached to. Here we have 3 examples. The original length of the gauge is defined as LO. By straining the object, the wire in the gauge gets longer and thinner, causing the resistance to go up. By compressing the gauge, the wire in the grid gets shorter and fatter, causing the resistance to go down. Strain is defined as the change in the length of the object divided by the original length of that object. Because this change is typically very small, the value is measured in micrometers per meter. Here we have another view of the same thing. The strain gauge is a piece of wire. Without strain, it maintains its original length and resistance. With a positive strain, the resistance goes up, and with a negative strain, because of the changing geometry of the wire, the resistance goes down. Now, this change in resistance is really very small, so it is difficult to measure that change using just an ohmmeter. So an amplifier circuit using the Wheatstone bridge and a high gain is used to convert this change into a change in voltage, which is then converted into strain value through a normalization process. So in conclusion, the manufacturing process required to build a metal foil strain gauge is rather labor intensive. A change in length in the gauge causes a change in resistance, which in turn is measured by an amplifier into a change in voltage, which is then converted back into a value for a change in length of micrometers per meter or microstrain. The basic design hasn't really changed that much in the last 75 years. The strain gauge is going to continue to be the go-to sensor for experimental stress analysis for decades to come.
Okay, thank you very much for this film. Back to the slides. Okay, so if you could see on the film, if we change the mechanical properties of the strain gauge, we will change the properties of the resistance. Because generally the resistance of the strain gauge is caused by difference of the length, difference of area, and this difference of the resistivity of the material. So if we connect all it together, we will have the equations that the resistivity is changed due to the change of the length. Okay, so we can the equations appears, but generally we've got the difference of resistivity, the resistance different, and the coefficient of the older sensor system. Okay, so it should be linear in the matter of fact. What is the problem of measurements of the strain gauge? Of course, we can use a typical Wheatstone bridge when we add a strain gauge as one of the resistors. Typically, the strain gauge ranges from 30 ohms to 1 kilo ohms. And as I said, it's more or less linear, but the resistance may change by a factor of a % of the full force range of the gauge, given the limitation imposed by the elastic element. So they are strictly on the manual, on the data sheet, they said the strictly forces, yes, that can be added to the strain gauge, and if we make a bad measurement and we add too much force, we can destroy the element. Okay, so it's mechanically sensitive. Okay, what are the another problem? As it was on the film, the changes of the resistivity of this element is very, very small. So we need to make a very high amplification system, but we can do something different. Okay, so for example, first of all, we can add another strain gauge. What for? This strain gauge is added to how to say it? Okay, the strain gauge is also very sensitive to the outside temperature. So if we would like to measure some, for example, movement or a force, it can't be dependent on the temperature generally. So to compensate this, we add another strain gauge that is uncompressed. So we do not touch it by the force, but it changes its properties due to the temperature, the same as this strain gauge that is stressed, this is compressed or something like that. Okay, so if we add one strain gauge that is not usable for the measurement, but it cause that the temperature differences are the same, so the voltage, the difference of voltage on the Wheatstone bridge will be not dependent on the temperature. Okay. Another, because as I said, the typical strain gauge differences are about 15 or 10 millivolts per volt. We need a high amplification. So we also can make a solution that we use two strain gauge. One is compressed, one is decompressed. Yes, and they are on the same temperature, so are temperature compensated. And if we add another strain gauge that is stressed, yes, in the opposite way that another, we will double the signal. Yes, so we've got more signal for the measurement. And in the same situation, if you add four strain gauge to measurement, we can double it. So we got the double by using double, but it can double this double. So we got 4 times more signal if we are use this strain gauge in this one. Okay, so if this one and this one is stressed and this one is compressed, so we can make a signal high. Okay, generally for some forces measurement, we are using strain gauge beam. So we've got a beam and we glue a strain gauge, one on the upper side, one on the bottom side, or 4 of them here, and using or we place strain gauge here that are just for temperature compensation, or we glue 4 strain gauge on the beam to have 4 times more signal on the Whinstone bridge. Okay, now I will try to I would like to show you some simulation of the Whinstone bridge, but not sure it goes. Okay, oh, it's working. Oh, perfect. So we've got a simulation of the Whinstone bridge. Okay, this is the Whinstone bridge. We've got more or less the same resistors here. This one is connected with the temperature changes, but this is just simulated as the X signal. So we've got the bridge. This is supplied by 3.3 volts, and you will see what happened here. And what is the problem of all the measurements is the noise. Yes, so we can add some noise here, and the noise will represent both some mechanical noises and thermal noises and so on. So generally, we've got the signal, yes, from the Whinstone bridge. So the sum of them should be 0. Plus and minus, the input voltage should be 0 at 20 degrees. So if we change the temperature, we'll change the difference. And here we've got the amplifier, the example of the instrumental amplifier we discussed last time. So we've got an amplifier with high impedance, yes, and another amplifier with high impedance, and a differential amplifier to have the output signal. I don't know what is the amplification ratio. It's probably 500 or something like this, because if you remember, this model of amplification depends only of this resistor. So I don't know how to calculate it now, but maybe it's not the problem. Okay, so if we can or we can't. Can we or we can't? Okay, we can simulate them. Sorry. Simulate. Okay, so we will see the V in, V out, and the output because the because the last part of this circuit is the two-step filter. Yes, this is the active filter, two-active filter here too, because we've got some noises, so we can filter them. So we've got the signal VFIT. So this is the filtered signal. So generally, we will see what's going on in this system. So first of all, I use some DC analyze. So we will see what's going on the input, output, and I hope. Why it's not calculated? Okay, so if you can see, we've got 5 millivolts as an input, so the difference in the Winston bridge, and we've got amplification up to nearly 1 volt after this amplification system, and after filtering, we've got similar, the same situation. Okay, if we change to the swap, we will swap the we will change the X value, and then you will okay, so you can see that if we've got, of course, very small input changes and larger output changes. So if you can see, it is linear because we change X, so it's the X value, so it represents the temperature. So we can see that the output value also changes, and it is more or less linear. Okay, what can we calculate? Can we calculate some noises, for example? Okay, so here we've got the. Okay, so we've got 2 noises. One is connected with the input. So I don't know this program. It's a matter of fact. Okay, so we've got the noise of the input signal. Yes. This is added by us in the simulation process. Here we've got I don't know how to use it. Okay, never mind. So this is the V-in signal, yes, and this is the noise. And this is the output signal. Yes, this is the output, and this is the signal after filtration. So you can see we can, using a simple active filter, we can filter the signal. Okay, so generally using transducer, using sensor, we have to amplify the signal and to filter the signal because our environment is not stable. Okay, so it seems to be all for today. Do you have any question? The next lecture, I will show you some solution for the flow measurement. So I will show you some films, maybe it will be more films next time. I will show you how to scientists.
Excuse me, sir.
Going to solve the flow properties measurements. Okay, yes.
Would we get any example questions for lecture exam?
No.
Like Christmas gift or something?
No, Christmas last. This was last Christmas. You probably can find the students from the last year, and they should have similar questions and similar tests. Don't worry, it is very easy. It's very easy. I'd like you to pass the exam. This lectures, this subject, it's not very important. Maybe it is more important to you to learn mathematics or something like this. It is just to your interest and to show you the solution, how to solve some problems. So don't worry, the test will not be very hard. I hope all of you will pass it. Okay.
Yeah.
Any other questions? If no, thank you very much, and we'll see you next week.
Thank you. Bye.
Thank you.
Goodbye.
Thank you.
Thank you. Goodbye.